Hi all, the purpose of this video is to go over Ampere's law. So our learning goals and objectives are to first understand when and how to apply Ampere's law, the second be able to explain the analogy between Ampere's law and Gauss's law. So we use Ampere's law to find the magnetic field, much like we use Gauss's law to find the electric field. And in both cases we can only do this if the situation is highly symmetric. So three common scenarios for when this can occur is current carrying wire. So in this case we'll have some current I, and then what we'll do is we'll pick an Amperian surface that is everywhere constant to the magnetic field. So at this point, part of it is you need to know the magnetic field is going to be constant at some radius, which we'll call R, from the wire. So in this case, it's going to be a current carrying wire, it's going to be a loop, and in Gauss's law, you always needed to know surface areas. In this case, you only need to know lengths. So this one's going to be a length of 2 pi r. Another case is a solenoid. So a solenoid is going to be something that has many, many loops, and what happens is that this carries a current I, and then what we're going to do is we're going to choose an Amperian surface as such. So it's going to be a length L, and then this length right here won't matter because by symmetry, the magnetic field, so here the magnetic field is everywhere around this loop, and then here the magnetic field is going to be going this way. So the contributions from these sidewalls won't matter, and then this is just going to be whatever length L, and then we're going to have, we could have a current carrying sheet, so something that has current uniformly infinitely thin, and then our Amperian loop would be the same sort of square or rectangle, and so we'll have magnetic field, or we'll have currents, and then this will be some length L, and this will now be 2L because the magnetic field is both all this way, so this is an infinite sheet, and this way, and we can see that by doing the right-hand rule. So that's why in Ampere's law, we have that integral b dot ds equal to mu naught I enclosed. So this is much like Gauss's law, so what we do is we pick a B field that's everywhere constant around our Amperian surface. We pull this B out, and then we just get B times whatever the length is equal to mu naught times I enclosed, and we can solve for the B field. All right, thank you very much.